This is the tutorial for lab number 3, which is the introduction to gamma ray spectroscopy. You will recognize the setup because this is our sodium iodide detector. I'll talk a little bit more about it in a moment. And this is the data acquisition electronics, and this is the computer that runs everything. But before we can do any kinds of measurements, we have to first get our samples. The samples are stored in this lead-lined safe, and you will see the red boxes that have my initials and the year that the sources were bought from Spectrum Techniques. And you'll take one and just bring it to the setup. This box has 8 sources, and the names of the sources are listed here on this sheet. And the principal gamma ray energies that come out of these sources are listed right here. We have low energy sources like cadmium 109, which has a gamma ray energy of 0.088 MeV or 88 keV. And then we have some up to high energy sources such as cobalt 60, which has 2 gamma rays, one at 1.17 and one at 1.33 MeV. So much more than a factor of 10 difference in gamma energies. And one of the goals of the first experiment is to show that the sodium iodide detection system, the channel number will be proportional to the gamma ray energy. First thing we want to do is to take a sample that is what I would call your base sample, cesium-137. That's the easiest one of these sources to look at. It only has a single gamma ray energy peak, so it's very easy to recognize its spectrum, and we will start with that. And by the way, I'm getting bombarded with gamma rays right now from all of these sources, but don't worry, these are not even licensed. They're such low level, and this box was delivered by a UPS driver. So even though there's radiation coming out at the moment, we don't need to worry about it. Now, we then locate the cesium-137. Here it is. The reason it's got a fuzzy cover is that we will use this in lab 3 to detect the absorption of its gamma rays in water. So this is sitting at the bottom of a beaker filled with water, and that has damaged the cover of the source. So we take it out and we put it in this plastic holder, and then we move the plastic holder to this top slot here and detect it. Now, since the gamma rays can penetrate through this plastic container, one of the mistakes of the first lab and the second lab is to have this container be nearby. Especially, I've seen students have the container right here like this, and that's a serious mistake, because I'm going to try to look at the spectrum of cesium-137, but all of these other sources are sending gamma rays into the detector and making a mess. So generally, when you take one of the sources, you can just take the box and move it over to the other lab table and then focus on the particular source that you're interested in. So this is the sodium iodide crystal. You don't see it, it's transparent. It's housed inside of this aluminum shield, and the purpose of the aluminum is to first protect the crystal, but also to make it dark. We don't want any visible light from the room getting into the transparent crystal, because it will then get detected by the photomultiplier tube, which is over here. So we've discussed this as a cartoon drawing, but this is physically what it looks like. The sodium iodide crystal is about that big and about that thick, and it's sitting right here. This aluminum shield, if you actually tap the front, you can tell it's much thinner than the side, and that's because we don't want the aluminum to absorb too many gamma rays that are coming in. And so we want this surface here to be, it'll be a thinner aluminum. So this aluminum then also has a little bit of protection against ambient X-rays and other cosmic rays that are coming into this building. But just to ensure that we have good shielding, we put this here and it's surrounded by lead. All right, so this is a lead shield which will surround our detector. Also, this lead shield will actually produce a feature in the spectrum that we have to be aware of. But at the moment, we're just going to show you how to operate this detector. There's only two inputs. There is a high voltage input right here. As you remember, we have to put a high voltage across the photomultiplier tube. That was covered in the lecture. And then we detect an output pulse. And that's the pulse detector, the current pulse that will come out of the tube. That gets detected by this and sent into the electronics, the multi-channel analyzer, which is here. We have a piece of tape here telling you how much voltage is the maximum that you can put on this. And in this case, it's 500 volts. So we're ready to go. You have to first turn on the instrument. So there's a power on switch here, and you have to turn this on first. This way, when this program starts to open up, it will then be able to recognize this piece of equipment. Okay, now we're going to go to the procedures of interfacing with the detector and plotting the data. And the program is called USX. That's the program from Spectrum Techniques. Now we'll double click on this USX icon and it will open up, and this is what the screen will look like. So we have to set up our detector, and it's useful to look at some of these icons over here. The first one is a start, so the green button here, when you click on it, starts counting. Once I start counting, there will be a red button which has me turn it off. I would say we want to go first to this settings window here, and the first thing you see is ROI, which is the region of interest. As you can see, there are regions of interest here coming from previous measurements, and we want to get rid of those. That's from someone else's work. So let's just clear all of it, and we see that that disappears. Under settings, we now go to high voltage, amplifier, and coarse and fine gain amplifier. So the first thing we do, we set the voltage at 500. It's already going to show up as 500 from the previous run. There are other detectors that run at 700, and then you would set this to 700. We just turn that on, and we put the voltage now onto our photomultiplier. The polarity, positive, these are default settings. We just go ahead and keep it that way. We see that we have coarse gains going from 1 up to 64. Without knowing anything, you would just pick a coarse gain somewhere midway, something like 8, and then we would have the fine gain down to 1. And we want 1024 channels, so that is already clicked, and we are ready to go with that. We've cleared our regions of interest, and we've set up a high voltage, and now we're just ready to start collecting data. So if you click this, you can see the data building up rather quickly. Remember, each one of these counts that's being stored comes from a voltage pulse that was detected with our photomultiplier tube. So the voltage pulse is amplified by the amplifier setting, and it is then, depending on the height of the voltage pulse, that is the channel number that it goes into. First of all, for some reason, the default of this scale here is a log scale. I prefer a linear scale, so let's do that. And now I'm off scale here. I've got a slide right here which changes the scale, and I can watch my counts grow on a linear scale. Let me go ahead and do it this way, you could still see the counts growing. So this is the main gamma ray coming out of our source, and this is a bunch of stuff that we will talk about in lab number 2. Since we're simply interested in the principal gamma at 662 keV, we're interested in this feature here. So I can take this slide here and move it out here, and then I will stop counting anything below that. That's my lower level discriminator, and I have an upper level discriminator over here, which would then eliminate any counts above that value. So I'm still collecting, and we can see that the gamma peak is growing in amplitude here. What we're interested in lab number 1 is the resolution of the instrument. There's a width to this peak, and that's because every 662 gamma ray that comes in, which has a fixed value, does not show up at the same channel. Sometimes it produces a peak at this channel, sometimes it produces a voltage peak in this channel, and most of the time it's producing a voltage peak which shows up in this channel. And where is that channel? If you just set your cursor here, so find out where that channel is, and that cursor is at channel 280. So the way our gain setting is set up, a 662 gamma ray is showing up in channel 280. So once you start to see a nice spectrum here, you can stop, and you can now set a region of interest, either going through the settings, but it's easier to just hold down your cursor here and slide it, and you will then set the region of interest that way. And if I just click on it, it will put the numbers in. The centroid of our peak is at 279.7, and the full width at half max is 21. Now, since these channel numbers are proportional to energy, delta channel, all divided by channel centroid, is the same as delta E over E centroid. So I can get the resolution or resolving power of my detector by just taking the full width at half max divided by the centroid. So let me do that on my calculator here. 21, which is the full width at half max, divided by 279.7, and I get a number which is 0.075, which is 7.5%. So the resolving power, the R value of the detector is 7.5%, which means I would not be able to detect a second peak which is within 7.5% of this centroid value. So that's not a very good resolution. I mean, that's compared to the resolution of your first lab where you did X-ray diffraction, you had less than a 1%, which was a much better resolution. This one is going to be poorer resolving power compared to the X-ray diffractometer. But this is how you would then go ahead and do the first part of this lab. You would take a certain gain value, collect data for long enough time where you see this reasonably shaped Gaussian peak, and then measure the resolution. And now what we're interested in is what this resolution depends on. So the first question is, does it depend on the voltage gain? Does it depend on the high voltage that you apply to the photomultiplier? And does it depend on the actual incident energy of the gamma source? So these are the questions you're trying to ask and answer in this lab. So you've made an image, and one can capture this image in two ways. If you go to the file part of the USX system, if you press save, it will save it as a spectrum file. You just give it a name and save it as a spectrum file, then you can call that spectrum back and do more analysis on it. You can use this region of interest, you can use the cursor and find energies of these other regions. You can do whatever you would do as if you had just taken the spectrum, okay? But in this case, we're not going to do further analysis on the spectra, so you might want to just save this as an image to put into your lab report, in which case then you can go to the snip tool, this icon. If you click this, you can select and create an image of this picture, and it will get saved as a PNG file or a JPEG file. So you can then input this image into your lab report. If you have questions on that, you can ask your TA. So let's get back to this image. The first question we want to know is whether or not the resolution, the R value, depends on the voltage gain. So I imagine that I've stored this image somewhere, and I can now click this off and start again. Let's change the gain. The coarse gain here is 8, fine gain is 1. Let's change the coarse gain to 16. What does that do? It takes a voltage pulse that would normally have gone into channel 280, that pulse height, and now I'm going to double the gain, which means I will double the height of the pulse. So we would expect that to end up in somewhere in channel 500 and something. And let's just go ahead and test that. We'll change the gain by a factor of 2 and now start to acquire data as we did before. And indeed, you can see that the gamma peak, the 662 keV gamma peak, is showing up in channel 538. So we've in fact close to doubled the channel number. So you can use this gain feature to move this principal gamma peak wherever you want to, from channel 1 to channel 1024. And we will see why we want to change that. If I want to look at these spectral features more precisely, as we will do in the second lab, I would want this principal gamma peak to be out here, so I could see all of these spectral features at lower energies with much better precision. And notice that it saves my region of interest that I did earlier, so I can stop it and I can clear the region of interest right here, get rid of it, and then keep going with my spectrum. Okay, so how would we put this peak out here somewhere? It was originally around 280. I want it to be in channel 1024, so I would want to triple the gain, so to go from 8 to 24. I can then just simply use the fine gain. Let me stop this and change that to roughly 2. And so I've got a coarse gain of 16, and this is a fine gain of 2. So that's a factor of 4. That would take a 280 peak and put it off scale. So that's too high of a fine gain. Let's make it 1.5. And so that's 1.5. That would make this 24, 3 times the original value of gain. Okay, and let's get rid of this. Let's get rid of the spectrum and start again. So indeed, you can see that the same 662 keV gamma can be in just about any channel we want by setting the gain. So the question is whether the resolution, the resolving power of the detector, depends on this amplifier gain. So as we discussed in class, we don't expect that it should. It basically took every incoming pulse and multiplied it by a gain value and moved it into a different channel number, and that shouldn't really affect the resolution of the instrument too much. But so let's go ahead and verify that. We can stop our spectrum right here. Let's take a region of interest and click on it. And now we see that the centroid is at 817, the full width at half max is 54. Let's calculate the R value, which would then be 54 divided by 817. That's 0.66 or 6.6%. But of course, I didn't really take a lot of data here. There is a slight change in the R value going from a gain of 8 to a gain of 24. So it's a minor effect on the resolving power. We went from 7.4% to 6.6%. Okay, so that's the first part of your lab. You would use maybe 3 gain settings. You can use a gain of 8, a gain of 16, a gain of 24, and record the R values for those 3 different gain settings. And you would collect data for a longer time than what I've done here. Okay, so the next point is to change the amplifier voltage and see how the resolution changes. So let me keep this value here. Let me keep the gain settings at what they are, and let's just go ahead and change the voltage of our detector. So I'll go up to here and change that by 10%. We'll make it 450. So we now know that because it's a lower voltage, the number of electrons that get produced in the photomultiplier tube is going to be less. So our initial pulse height is going to be smaller. So we expect the signal to move down to a lower channel number. But the question is, does it have any impact on the resolution? So we would now click this off, go back, and we see that by lowering the voltage from 500 to 450, we've dramatically changed the pulse height, and because it's now showing up in a much lower channel. So you would collect data a little bit longer. There's a preset time that one can change. Right now it's set at 360 seconds, which means that the maximum time it would collect would be 6 minutes. I can set that to any value that I want. Let's stop. And then we'll do the region of interest, click on it, and we have a full width at half max of 24 and centroid 283.6. So if I put that into a calculator, that's 8.1%. So I kept the gain settings fixed and I changed the voltage. When it was out here, that was at 500 volts. The resolution was 6.6%. When I lower the voltage, I get a poorer resolution. The R value is now, it's a broader function. This full width at half max is now 8.2% of the centroid. So indeed, you increase the R value, which means you diminish the resolving power of the instrument by changing the DC voltage on the photomultiplier tube. All right, so that's quickly going through the second part of the lab. And now we will go to the most important part. Let me stop taking data and let me clear the regions of interest here. Oh. Let me clear all. And I want to take this back up to 500. I want to move these discriminators out to the end points. And I want to put in a larger energy gamma source. I want to keep all the settings fixed, and I want to put in the different sources, and they will end up on different channel numbers, and I want to measure the resolving R value for each gamma energy under fixed gain and fixed voltage settings, and to see if there is a change in the resolution as a function of the incident gamma energy. This turns out to be the most important part of the experiment. So what we have to do is we have to take our highest energy gamma sources and put them into the highest channel numbers so that the lower energy gamma sources show up on one of these channels, and I don't end up with a high energy gamma source off scale. Here is the list of the energies of our gamma sources. You'll see that the cobalt 60 has the highest gamma energy, 1.33 MeV. So we want to put that one in because that's the highest gamma value, and we want to put that into the highest channel number that we can. So I go back to my sources, I put cesium-137 back in, and I look for the cobalt 60, Here it is, and I put it into my holder. All right, so now we have the cobalt 60. We had the gain settings so that the cesium-137 peak was out here. So if I just keep those settings, the cobalt 60 gammas are going to be off scale. So I have to turn this down and go back to a coarse gain of 8, which put a 662 peak in channel 280. So a 133 peak would be in channel 560. So I can go ahead and multiply that by another factor of 2, but let's just, to be on the safe side, let's just guess something like 1.8. Okay, now, all right. So these are the two gamma energies coming out of the cobalt 60, and I made a pretty good guess for what the gain value should be to put this highest energy peak in the highest channel possible. Notice I still need to measure the resolution here, so I need to get the whole gamma spectrum here, so I have to, and so if I had picked a higher gain, I would only have half of this Gaussian looking peak in the channel. So I've got the full peak here, so this is actually a pretty good choice of gain. Now, you would count this for a longer time than I'm doing here, but I'm just going to stop it and show you one of the main results of this lab. So I'll stop counting, and we will do a region of interest. And we see that the centroid is at 966, almost 1,000, and the full width at half max is 43. So I don't even need my calculator. I could just divide 43 by 1,000, and that's giving me the resolving power. So that would be 0.043 or 4.3%. So you see that already for cesium-137, we were getting something like 7% R value. Here we're getting 4%. So we see that higher energy gammas actually get resolved much better than lower energy gammas. And you will then keep these gain settings and then put all of your sources, or at least 4 or 5 of them. We'll have 2 high energy peaks here. We'll have the cesium-137, which is at 62, and we can put in a low energy gamma down here. And then we will have a full range of energies, and we can plot the R value for energies as low as from 88 keV up to 1.3 MeV. The second most important part of this lab is to show that the centroid, in terms of channel number, is going to be proportional to the energy of the gammas. So we know what those energies are. We have our sheet, and we can make a plot of the actual gamma energy versus the channel number that it is in for a given set of gain settings. So right now, this 1.33 MeV gamma is sitting in channel 966. I can make a plot of gamma energy versus channel number for all of my sources, and you will see that that will be a straight line. So that's going to say that the instrument is linear in the gamma energy. That means what I'm measuring in terms of channel number will be proportional to the gamma energy. So we will show that the resolution is better the higher the gamma energy, and we will show that the instrument is linear. Let me just go ahead and show you a lower energy gamma. We're keeping all the gain settings fixed. Let's just get rid of this, and I will take my source out, putting the cobalt 60 source in. I'm looking for a low energy gamma. You see cadmium 109 has a gamma energy of 0.88 MeV or 88 keV. That will be the lowest energy gamma that you will measure out of these sources. So let's put that in. We'll put that into our instrument. So obviously you should already know where it's going to be. 1.3 MeV peak is over here with the gain settings, and 88 keV peak should be down here. Let's go ahead and start counting. This low energy peak is going to be an X-ray. This has to be the principal gamma ray energy at 88 keV, because that is the highest energy coming out of our source. This thing, at the moment, you don't know what it is, but I'll tell you that it's an X-ray that's coming out at lower energies. It's occupying a lot of time here, so I'm just going to get rid of this, and it will move my discriminator here, and notice that it no longer counts any pulses that have energies below the discriminator setting. So it's only building up count totals for the principal gamma of cadmium-109, which is at 88 keV. You would, again, get a really nice spectrum here, so you would measure for longer than what I am doing. We've set our gain so that we can see the lowest energy gamma and the highest energy gamma with a single set of gain settings. All right, let me go ahead and stop this, and I'll do a region of interest, and then we'll end this first tutorial. So we have a full width at half max of 12 and a centroid of about 74. So when I go to my calculator, I get 0.16 or 16%. So do you see that the lowest energy gamma has an R value of 16% and the highest energy had an R value of 4%. Remember, the lower the R value, the better you are able to discriminate nearby gamma energies. So this is a poorer resolution. We go from 16% all the way to 4% with the highest energy gamma. So that summarizes this first lab. I think we've covered most of the basics. If there are any questions that you still have, you can always talk to your TA. I just want to say that before you stop your experiment, you should turn off the high voltage. That's important. And then you can click off the USX program. And be sure to turn off the power on the instrument. That's important. And then we're done.